all of this from Mr. Bean up until right here. So let's do some notes with this. The idea of this linear approximation is that if you're close to, right, if I have some curve and I know a point on that curve and I draw my tangent line, anything close to that point, my tangent line would be a pretty good estimate. I'm guessing that my tangent line way down here would be a very bad estimate for that point because it's very far away. But if we're looking at something close, right, I think anything in that red circle would be pretty close. The further away I get from my the point of tangency, the less likely that it's going to be a good estimation. And I mean, this curve might come back down here and be like, oh, but it's perfect way up here. Well, that's just coincidence and luck. Yes. They actually use this a fair bit in engineering. That they use linear approximation for sine of x for very small values of x in radians. In fact, I've noticed this on provincial exams. They try to avoid this because they actually can't tell if the student did it right or wrong. So for example, here's my example on the calculator. I've got a question that looked like this. Sine of x equals 1/7. Okay? You know that you should find this by doing the inverse. But some student makes a mistake and doesn't hit the right button and just does this. Okay. So obviously the person that did the wrong method should get it wrong, and you said round to the nearest hundredth. Well, I go to my calculator right now, and I'm like, the right answer is right here, sine inverse of 1/7. Oh, and you had another kid. Here, let's just have fun with this. You had another kid who said, I'm just going to circle the answer. I'm going to just go with 1/7. What the heck? Let's look at those answers here. Sine inverse of 1/7 is, oh, I'm in degrees. Hit my mode, back to radians. Type that in again. Ah, 0.143. The kid that just decided on 1/7, oh, 0.1428. Sine of 1/7. Oh. And if it was to the nearest hundredth, all of them would get it right, no matter which method they use. So this is not a very good question. Sometimes on the grade 12 provincial exam, it's sort of like, oh, we shouldn't have this question because all three of these wrong methods end up with the right answer. Okay? So, why does this happen? Well, find the linear approximation of f of x equals sine x at x equals 1/7 and compare the answer with the actual answer. Well, the equation of this green line, it goes through 0, 0, right? 1/7 is pretty close to 0, 0. I can easily figure out that the derivative of sine is cos, and the slope at 0 is 1. So I've got my point 0, 0, and I've got my slope of 1. My equation is just y equals x. That's that green line. Which means a really good approximation for sine of 1/7 is 1/7. Because if I'm using the approximation, well, my y value should be equal to my x value. So everything really close to 0 is close enough to just use the value. So like, approximately, what is sine inverse of 1/8? I'd be like, oh, I think it's 1/8. Or I'd be impressive and I'd change it to like 0.125-ish. Right? And then you say, well, is sine of 1/8 close to that? Sine of 1 divided by 8? Oh, I was actually correct to 3 decimal places. The closer I get to 0, like sine of 111 is going to be pretty close to 0.09 repeated, and I can check it. Oh, I was correct to 3 decimal places. I had 0909 and it's 0908. Like, oh, that thousandth, right? And if you're in engineering, you're like, oh, that really doesn't matter anymore because those significant figures, so you were close enough. So you'll see sometimes in engineering, they will use this as like, hey, for mental math, for all intensive purposes, that's close enough. You're only going to 3 decimal places. If you, instead of doing sine of 111, you just use 111. Because the linear approximation says that close to 0, my tangent line is y equals x. Which means the answer should be really close to whatever you put in. And the actual values are super, super close. Which is kind of cool. It's kind of cool, but also kind of disappointing. I'll share my disappointment. Because, of course, I noticed this at some time in my math career, and I was like, oh, it's cool that sine of 1/7 is so close to 1/7, because I had the decimal memorized, and I thought I was realizing something so neat and important, only to find out it's true for 1/8, 1/9, 1/10, like, I thought I found 1/7, and it was like, oh. But it works for all of them. And it's kind of disappointing once you come up with like a calculus rule like this, it sort of says, well, this is why. It's like, oh, I thought I found something really cool. All right, next question here. Use the table of values. This is a favorite AP style question. A little bit devoid of context, so you're not allowed to use any of your extra calculus. To find a linear approximation for 1.9. That's what happened. I marked you absent.
I wasn't here at the start. I was having photos done.
Okay. But now in the new seating plan, you're actually 1 over, but that's fine for today. That makes sense. Well, I didn't mark you late. I just marked you absent, present. We're good. So what do we know? We know the closest value to 1.9 would be 2. And we know that f of 2 is 14. We also know that f prime of 2 is 9. And now you have a point and a slope. So you can use y minus y1 equals mx minus x1. That's your linear approximation, because that's your equation of your tangent line. This is the equation of tangent line, aka linear approximation. This is like a favorite pastime of mathematics. Like not using just one word to describe something, but coming up with a whole bunch of different words just to be like, oh, you thought you were good at x-intercepts? Well, can you find zeros? You're like, that is the same thing. How about solutions? Okay. How about the roots? Oh. Like, we keep coming up with a new word and we're like, technically, if we want to be fussy mathematicians, you were like, you only use x-intercepts on graphs. And we use zeros on equations of functions. Solutions when there was no y to begin with. Like, whew. Right? Now we've got linear approximation, same thing as your equation of your tangent line. So now you could plug in the 1.9 and you get the 13.1. Why do they like this as a multiple choice question? Because you would read this question and they would have as answers 13.01, 13.1, 13.11, 13.011. And if you were guessing, would you have any hope of being like, it's truly a 1 and 4 if you're guessing. You're like, I don't know. Well, what I would have. Oh, awesome, thank you. So they like these questions for multiple choice because they're truly, you either know how to do it and will get it right, or you're going to guess and have a 1 in 4 chance. All right. I'm actually going to stop that first video there.